Thing? Luke? Nope. Blake?
I'm sorry. Can you do number 44?
44? Yeah, of course. Copy. Shoot. So it says find the product by foiling and then leave your answer exact in standard form. So I FOIL this out. I got 2 times 1, that's 2. 2 times I root 3 becomes negative 2I root 3. 3i times 1 is negative 3i. Negative 3i times I root 3 is positive 3 root 3i squared. So when I combine my like terms here, the I squared becomes a negative 1. So this is my A, and then this part becomes my B. I guess I'll make it a subtraction symbol. So 2 root 3 minus 3i. Oops, that's a plus. So like A and B. They're just irrational numbers.
Wait, can you like repeat that last step again? Just like say it out.
So I have
like write anything, just
2 minus 3 root 3, right? That's my A term because there's no i's attached to it.
Yep.
Now it's fine that it's 2 different things. It's just an irrational number.
Oh, and then
right?
Okay, yeah.
And then I take the negative out, and then everything else is the inside with the I on the outside. So that's like my B term. Again, it's okay. It's just an irrational number. No biggie. Cool? Ava.
Can you do number 22?
22? Okay. So the first thing we want to do is the absolute value. So that's going to be 3 root 3 squared minus 3 squared, plus 3 squared. So 3 root 3 squared is 3 squared times root 3 squared. So 9 times 3 is 27. And then 3 squared is 9. So that's going to be 36. So that's 6. Okay with that?
Yeah.
And then if I plot these, I have 3 root 3 on the x direction and negative 3 in the y direction. Or if you prefer, we can call it in the real direction and the imaginary direction. So what I have here is, that's my theta. So this is my alpha, and that's 360. So theta is going to be 360 minus alpha, where alpha is the tan inverse of the absolute value, negative 3 over 3 root 3. So let's go and make sure that we're in the appropriate mode. For this problem, they asked us to between 0 and 2 pi. Oh, this is actually a unit circle angle, isn't it? Hi, thank you.
No problem.
Maddie Frazier, for you. Right, so this is y over x. Just do it on the calculator, it'll tell me. I have to be a little bit careful here with your parentheses. So 30 degrees, which is pi over 6. So this would be 11 pi over 6. So then I'd say I have 6 times cosine 11.
How did you get the 11 pi over 6?
Well, this was 30 degrees, which is pi over 6.
Yeah.
So 2 pi minus pi over 6 is 11
okay.
pi over 6. Is that okay?
Yes.
I just couldn't remember in my head what that was, so I just did in the calculator in degree mode because it was be super obvious. Like what? Okay, that's good. That's what I needed.
Okay, thank you.
Yeah. Yeah, Raylan?
Can you do 27?
Yeah, so same thing, just we're not going to be able to get a exact answer out of this one. This one will just be a decimal. So we have 4 squared plus 7 squared. So 16 plus 49. So that's root 65. And then that's 4 over and 7 down. So again, that's my theta, so that's alpha, and that's 360. So theta is again going to be 360 minus alpha, where alpha is tan inverse the absolute value of negative 7 over 4. And we wanted that in radians mode, since wanting our answer between 0 and 0 and 2 pi. So I guess I should probably write that as 2 pi, huh? Great googly moogly, Mr. Gulick. You know, like 2 pi, 360, whatever. You guys will get it. I hope by this point, right? Notice that I'm doing the absolute value in my head rather than typing into my calculator. So 523. So root 65 times cosine 5.23 plus I sine 5.23.
What's the previous one you just did in radians?
They're all in.
They're all in radians.
Well, when I did I didn't remember what, this was an exact answer. I recognized the 3 over root 3 as an exact answer, like a unit circle answer. So I had it in degree mode to get because I knew the degrees better than I know the radians by decimal.
Okay.
Like if I was going to look at pi over 6, I wasn't quite sure what the decimal for that's going to be, but like 30 degrees, I know 30 degrees. And then I just convert everything back into radians is why I did that. So yeah, I left it in degrees because it was going to be easier to get the exact answer out of without having to go to the unit circle for me. Is that okay?
Yeah.
Okay. So it's just kind of me being, I don't know, lazy. Is it lazy? Efficient. Alex. Sure. It's on the next page. All right, so 49. Okay. These guys are mental math problems now at this point, so all I need to do is multiply the r's, and then I'm going to add the thetas. Done. Is that cool? That's lovely, isn't it? Yeah. Maddie.
You do that again.
Yup. So this is just a calculator problem. 7 pi over 12 is not a unit circle number. It's close. Oh, is it? Let's check real quick. $105. No, not a unit circle number. Okay, so it's just calculator. So 8 times cosine 7 pi over 12. I know my calculator is still in radian mode because I just put it in there a moment ago. So there's my A. And there's my B. Oops. Would be if I typed sine instead of cosine, you big dummy. There we go. So a negative 2.07 plus 7.73 I. Is that okay, Maddie? The angle's in radians. If I'm going to do cosine or sine of an angle, and the angle's in radians, I better be in radian mode. That's all. Anise. Sure. So I'll start with the absolute value. So 25 plus 25 times 375. So 25 plus 75 is 100. So that's just 10. So there's my theta. That's alpha. So that's pi. So theta is going to be pi minus tan inverse of 5 root 3 over 5. That I recognize as a unit circle value. I think that's 60 degrees. I'll just double check real quick. Oops. Do that. Yeah. So this becomes then 5 pi over 6. No. 4 pi over 3. No. 60 degrees is a sixth. Or is a third, excuse me. 2 pi over 3. Cheapers, creepers, Kulik. It's just me trying to do this unit circle stuff without my unit circle. Is that okay, Anise? I went 5 on the x and 5 root 3 on the y. So I just need to know really what quadrants it's in. I don't really need to know exactly where it's at. Obviously, that's not to scale there. Like 5 times root 3 is bigger than 5. And it certainly doesn't look like it from the picture, but like, whatevs, you know? I don't really need to plot it. I just need to be in like the right vicinity so I can draw my picture to know where I'm adding or subtracting. You know what I mean? Okay. Allie?
Just going back to 39, so just to understand kind of what we're doing, are we just doing cosine 7 pi over 12 to find the answer and multiply that by 18?
Yeah, did I press 8 in my calculator instead of 18? Yeah, so that's why my numbers were weird. If you're like, I didn't get that.
Okay.
Yeah, so that's just wrong.
Right.
But like, you get the idea.
Okay.
8, 18, tomato, whatever. Like I knew what I was doing. I just pressed the wrong buttons. Actually, I just didn't read it correct. I don't think it was a button issue. I think I legit thought it was 8. Ugh. All right. Blake?
Just one more question, number 48.
So I want you to divide these by rationalizing the denominator. So 2 minus 3i, and then 1 minus I root 3. To do this, I'm just multiplying by the conjugate, so 1 plus I root 3. I'll multiply that top and bottom. When I FOIL the numerator out, I get 2 root 3i minus 3i, and then minus 3 root 3i squared over 1 plus 3. So I combine like terms and simplify my numerator. I have 2 plus 3 root 3 over 4 plus 2 root 3 minus 3 all over 4i. Write it that way. So I think that's probably what it
mean, I all the way out on that, like I'm very far away.
Why did I do that?
Why didn't you just continue?
So I call it A plus B I.
Okay.
Right? So this is my A, this is my B, and put my I out the end. Same thing as leaving both I's in there, but like then you're not in A plus BI form technically, so I'm just trying to follow the directions as like precisely as I can. Yeah, give the answer that they want, not the answer you got. Okay. Today, we're going to pick up where we had left off. So we are now in section 11.3. Excuse you. It just sounded like a fart. And those are hilarious. Okay. We're going to be talking about powers and roots of complex numbers. We're going to start with powers. And it's much easier to talk about these in the trigonometric form. So just note, say we have some complex number, r times cosine theta I sine theta. If we want to do that numbers squared, remember that's the same thing as z times z, right? And using our formula for multiplication, that's going to be r times r, and then theta plus theta. Everybody's okay with that? If I do z to the third, I could think about that as z times z squared, right? So that would be r times r squared, so r to the third, and then theta plus 2 theta, so 3 theta. And at this point, does anybody see the pattern? That's super, super easy. We call this guy, has a name, this is called Demarvare's theorem. So we have for z equals r times cosine theta I sine theta. Z to the n is equal to r to the n times cosine n theta plus I sine n theta. Okay, so let's do this one. So we have 5 times cosine 14 degrees plus I sine 14 degrees to the 5th. What do I get? Use Demarvare's theorem. Five to the 5th times cosine of 5 times 14 plus I sine 5 times 14. Now we can simplify this down. 5 to the 5th is, who knows that? Nobody. Nope. Oh, did you say 3,000 or 2,000? Oh, my apologies. I thought it was a 2. You used your calculator?
Oh yeah, that's very impressive.
I'm not a fast thinker, but I can put the numbers.
I wrote it down. So there we go. Boop. What if we wanted this in standard form? Then we just ask our calculator to do that, right? We just got to make sure we're in degree mode. Yep, I moved it back to degree mode at some point. So I have 1,068.8 plus 2,936.5 I. Right, depending if the directions ask for your answer in standard form or trigonometric form. Correct! The first box is your trigonometric form answer. The second box is your standard form answer. What if we'd given you the problem in standard form and asked you to do this? What should I do now? Well, I'm going to convert it to trigonometric form. 49 plus 36 is 85, right? Oops. So 319.4-ish. So what do I have? So I have square root 85 to the 10th times cosine of 10 times 319.4 degrees plus I sine 10 times 3.194 degrees. So that's really the same thing as 85 to the 5th. Why is that? Square root is the same thing as an exponent to the 1/2. Exponent of an exponent you multiply. 1/2 times 10 is 5. Yeah. Yeah. And then 3,194 and if you want you can what do we say? Coterminal that down to something between 0 and 360. And you could do 85 to the 5th on your calculator if you wanted, depending on what the directions we're asking for. You know what I mean? And if you want to take this back to standard form, easy enough. So you got that monster. Ay caramba! That's a Simpsons joke. Do people still watch The Simpsons?
Not the new stuff.
And then that minus that stuff, I. I'm just not going to write it all down because, like, quite frankly, woof, that's a lot of numbers. Mr. Kulik picked too big of values. He should have been sneaky and picked something whose R was 1, so it just was like, I can do this now in my head. Right? Like, had Mr. Kulik done, you know, I can do that in my head. How?
Yeah.
Well, okay. So the R here is 1, so it's just going to be 1 to the 50th. No big deal. And then this is at 40, the theta here is at 45 degrees. So there's, let's make this 40 to make it a little bit easier. Is at 45 degrees. So there's 8 of these in one rotation, right? So if I do 5, that's basically 5 times around the unit circle. So it's going to end up right back where it started. So it's literally going to equal itself. Demarvare's theorem, guys.
Who is Demarvare?
He's a mathematician.
He's a French mathematician that discovered the theory.
I think that about sums it up.
That should be an extra credit question.
Yeah.
Random facts.
Finish the last name. You just put the dot and we'll put the last second.
Oh, I'm trying to think.
5 points.
All right. So we have Demarvare's theorem. We can see it's super useful. We can modify this now to deal with radicals. How can I do that? Well, what's the same thing as an nth root? The exponent 1 over n. So if I apply Demarvare's theorem, I should get this, right? Not quite. Why not?
That's a really good question. Why not?
We have to worry about coterminal angles since we're getting smaller, right, instead of going forward. So really what we have is the following. So I'm going to write this now as the nth root of r. It's still the same thing as r to the 1 over n. God bless you. You're welcome. See, kids, that's manners right there. Blake was raised right. Not to you, to your parents. You can relay my compliments. Yeah.
Mr. Kulik approved of their parenting.
No, I would say you are well parented because you have excellent manners. You're welcome. Anise.
May I?
Yes, please do.
Yeah, that was really good.
I know. I appreciate where you went there. It's quite funny. Okay. So we have, again, a version for us, whether we're dealing with things in degrees or radians. It's the same formula, though, right? The only difference is the radians. The takeaway here is if I take an nth root, I'm going to get n different solutions. Which shouldn't be surprising, right? Let's do an example to kind of hit this home. Sound good? So let's say we want to find the cube root of 3 minus 2i. What should I do first? I convert this to trigonometric form so I can apply my Demarvare's theorem, right? Just want to double check we're still in degree mode. 326.31. So we can then say this so far so good. Step 1, we're now in trigonometric form. Step 2, what do I do now? Well, We do the cube root of the square root of 13. Yucky! It's okay, guys. Then we have 326.3 plus 360k over 3 plus I sine 326.13 plus 360k over 3, where k equals 0, 1, and 2. How do I know I'm stopping at 2? Very good. Right? The n is the root. Okay, so if I sum this up then, what do we got? We got the 6th root of 13. Whoa, Mr. Kulik. Hold on, where's the 6th root coming from? Square root is 1/2, exponent 1/2. Cube root is exponent 1/3. Exponent of an exponent multiply. 1/3 times 1/2 is 1/6. Back to root 6. Right? See it now? Okay. So when k is 0, I get that. When k equals 1, 360 plus that is 686.3. And when k equals 2, I have 326 plus 720. So that's 1046.3. And again, if you wanted to, this question, since it was given your answer, your question was given to you in standard form, probably wants our answer in standard form. So we just go to the calculator and pound that out for each one of those 3 when I'm done. Do you remember how to do a 6th root on your calculator? 2 ways you could do it. You could do like 6 and then press the math button. Go down to the command 5 that's like the xth root. So you do like 6 root of 13 like that. Or you could do 13 to the 1/6 power. Either way is fine. Everybody's okay doing that? Hopefully ringing some bells. Okay, so that's, yeah, no big deal, Mr. Kulik. Find the 4th root of 16. What's that? Two, incomplete answer. How many answers should I have? I should have 4, right? The degree of the root should be the same. Oh, Mr. Kulik, are you joking? No, man, I ain't joking. All right, convert this to trigonometric form. 16 is here, right? So the r is 16 and the theta is 0. So 16 is 16 times cosine of 0 plus I sine 0. So the fourth root of 16 is equal to the fourth root of 16 times cosine of 0 plus, we'll do it in radians this time, 2 pi k over 4 plus I sine 0 plus 2 pi k over 4, where k is equal to 0, 1, 2, and 3. So fourth root of 16 is just 2. For 0, I'm going to have cosine of 2 pi, or I'm just 0, right? Everybody's cool with that? Well, that's just 2. When k is equal to 1, I'm going to have cosine of 2 pi over 4, or just pi over 2, plus I sine pi over 2. Well, that is, cosine there is 0, but sine is 1, so I'm going to have 2i. When k equals 2, I'm going to have cosine of pi plus I sine pi. There, cosine of pi is -1, sine of pi is 0, so I'm end up with -2. And then last one, cosine of 3 pi over 2 plus I sine 3 pi over 2. Here, cosine 3 pi over 2 is 0. Sine 3 pi over 2 is -1, so I have -2i. Whoa! So these guys are my answers in standard form. The thing to the left would have been my answer in trigonometric form. This was a good one because I could do the conversion to standard form in my head. I didn't have to try to type in a million things in the calculator over and over and over again. What do you think? This is the hardest thing that we have to do in this chapter, I think. And it's not even that hard. It's just like you're using a formula. So that's the good news, right? That there was nothing in this chapter that was too hard. You ready for the bad news now?
Oh, it's, yeah.
Okay. I know that's a lot of them. That is a lot. Yep.
I guess there's just a slight bit of repetition then. That's 55 problems. It's a good amount.
Didn't do the ones from last week.
It's actually 66.
So get ready. I like
Wait a minute, wait.
65 starts at 0.
What?
65, 66, 67, 68, 69, 70 gets you to, I think it's 56.
Oh. I'm just gonna skip 65 out of spite.
Blake, I'm gonna mark you down for it. Of all the problems to skip to, we're gonna skip the first one, not the last one. All right. Next up is the homework quiz. You guys want to clear your desks? We'll get this going.